right, let's take a look at example 3.82. So when a train's velocity is 12 meters per second eastward, relative to the ground there, raindrops are falling with a vertical velocity with respect to Earth that make traces that are inclined at 30 degrees to the vertical on the windows of the train. And the first part here, A, says what is the horizontal component of the drop's velocity with respect to the Earth and with respect to the train? Okay, so if the drops are falling vertically, the velocity relative to the ground of the raindrop is going to be 0. So we have the drop relative to the ground is going to have a 0 I hat velocity, but it is going to be moving some terminal speed here. I'm going to call it VT in the J hat direction, and it's moving down, so I'm going to make it negative. They do tell us that the train, our moving frame, is moving at 12 meters per second east, so 12 I hat, and it's not moving vertically, J hat. The raindrop then is going to have a horizontal component here and a vertical component here. It doesn't take much for me to go, well, this number, in order for us to have our equation that this plus this has to equal that, I can figure out that the horizontal component then of the raindrop must be negative 12. Another way I can think about doing this one is I can set this up as being like, okay, this is going to be V sine 30, and this is going to be V cosine 30 for that raindrop relative to that window. The benefit for this is I know this number to be 12, so I can figure out what that V is. If I know that V, I can find the vertical component of that raindrop as well, which is what they're going to ask me to find here. So that's going to be kind of our pattern for solving that. So we're going to see that the raindrop is moving this direction relative to the train, so negative V sine 30 I hat plus, and it's moving down here, so negative V cosine 30 J hat there. Okay. So we're going to try and find this V because that will tell me what the horizontal component and vertical component are, which is the same as that vertical component, because these are the 4 parts they want me to find of this raindrop. So let's go ahead and start solving for that. So in my I hat direction, I have 0 is equal to negative V sine 30 plus 12. So we'll move this to the other side, divide the sine of 30 over, and we find out that V is 24 meters per second. So that is the velocity of the raindrop relative to the train. That is this value here, which I think, let me just double check. What is the magnitude and velocity of the raindrop with respect to Earth and with respect to the train? So this is the velocity of the raindrop with respect to the train. Is going to be moving at 24 meters per second. In order to find VT, or the terminal velocity, velocity of the raindrop relative to the ground, okay, so now I'm going to have negative VT is equal to negative V cosine 30 plus 0. So I'm using the J hat direction of that equation. And I find that the terminal velocity of that raindrop, I'm assuming it's at terminal velocity, that this train is not moving through the clouds here, is 20.8 meters per second. So to answer all of these parts of this question, because they asked a whole bunch of things, A wants to know, what's the horizontal component of the drop's velocity with respect to the Earth? 0. What's the horizontal, and then with respect to the train? So that's going to be 24 sine 30 with a negative on it, so it's going to be 12 meters per second in the negative direction, so west. And then what is the magnitude direction? Oops, I'm sorry. What is the magnitude of the velocity of the raindrop with respect to the Earth? That's going to be our 20.8 straight down. And with respect to the train, that's going to be our 24 meters per second at that angle of 30 degrees. Nice relative velocity problem there, huh?